Welcome back to 2.6 Examples for You. When we're looking at related rates, we want to think about what geometric shape we can put this into. So are they talking about a cone, a sphere, a circle, area, if they're talking about a right triangle, etc. So when we read this, it says an airplane is flying at an altitude of 6 miles on a flight path that will take it directly over a radar tracking station. Oh my gosh, these problems are so exciting. If S is the distance from the plane to the station and it is decreasing at a rate of 400 miles per hour, when S is equal to 10 miles, what is the speed of the plane? All right, so now that we know that, let's go ahead and put in things that we know. We've got a station. They're talking about the altitude. Remember, the altitude is a perpendicular. Okay, so that would be a right angle. That altitude or the height of the plane is 6 miles. Here's our plane up in the air. And they're talking about this guy right here as being, that distance is S. So let's go ahead and rename this station so we don't get them confused. So that distance there, this is our plane. So we're going to call this X because that is a horizontal distance. I always like to use Y's for my verticals, X for my horizontal. So because of this altitude word, it does tell us it's a right triangle. We are able to look at that as our x squared plus, since this altitude is not changing, the plane is not declining or inclining, I can actually put the 6 in at this moment in time. That is equal to our distance between the plane and the station of s squared. When I take the derivative of x is 2x dx dt. The derivative of 6 is 0. The derivative of s squared is 2s ds over dt. We want to actually find the speed of the plane. So if we look at that track that the plane is on, here's our plane. And our plane is traveling this way, so that speed is actually going to be dx over dt. That change of miles per hour, okay? So we want to actually solve for dx over dt. So if we divide through, we're going to have dx over dt is equal to 2s ds dt over 2x. So we can cancel out those 2's. So we have s over x. And you can write the ds dt beside it. You can write it on top. It doesn't matter. It's all multiplying your x. That's a t, by the way. All right, so now let's find out what values we have. They've told us that s is 10. So this right here is 10. They've told us what ds dt is. It is decreasing at 400 miles per hour. Remember, whenever you see miles per hour, you know that is a rate of change. So that's ds over dt or dx over dt because it's that distance from the station that's changing. It's ds dt. So we also know that. What we don't know is x. So if you look back at our picture here, my wonderful picture, we know that the altitude is 6. At this moment in time, we know this distance is 10. So using our Pythagorean triples, we know that x at this same moment in time is 8. So we really do know what x is equal to. So let's plug in all of our information. dx over dt, which is that speed, miles per hour. S was 10. ds dt was 400, and it is decreasing, so negative 400, all over x, which is 8. When we put that in our calculator, or we can use our brain, it all works out the same. We end up with negative 500. It will be miles per hour. Okay, so looking at what we have right now, it's negative 500 miles per hour. This is actually a velocity. It's telling you the direction at which your plane is traveling. Okay, that distance is decreasing. So they want the speed of the plane, so don't forget speed is the absolute value. Speed, not speep. Okay, speed is equal to the absolute value of velocity. So our answer is 500 positive miles per hour. And note, you can do your notation either way. Write out your miles per hour or mph. Don't write m over hr because m would be meters and then we would be in big trouble. So 500 miles per hour is what the speed of our plane is at this moment in time. Okay, so we have another example. This is the cone. The formula for the volume of a cone is 1/3 pi r squared h. Find the rate of change of the volume if dr dt is 2 inches per minute and h is equal to 3r. They want to know, find that rate of change in the volume when r is 6 and r is 24. So notice they've talked about r dr dt. They have not mentioned h or dh dt, so that means h has got to go. Lucky for us, they've given us what we can use as a substitution. This nice handy little equation that they give you, and remember they won't always give you this equation, so please put into your memory banks the volume of a cone. H is equal to 3r, so I'm going to substitute that in there, and I am going to simplify my equation. The 1/3 and the 3 are going to cancel each other out, so I end up with pi r cubed. Always simplify your expression down before you differentiate. Make sure that you're not plugging in numbers for those variables until after you differentiate. If it's allowed to change, it has to stay a variable. The derivative of v is dv over dt. The derivative of pi r cubed is 3 pi r squared dr over dt. They're asking us to find the rate of change of volume, so they're asking us to find dv over dt. They're asking us to find it when r is 6 inches, so 3 pi times 6 squared. dr dt is 2 inches per minute, so put that in there. Simplify, it's okay to leave it in terms of pi. So that would be 216 pi. Always put your units. Remember your units on your volume. Look at your units of your volume up here. You've got r squared h, so that's going to be cubic inches. Cubic inches, let's write inches cubed. Inches cubed over your time, which is in minutes. Now part B, we want to know how the volume is changing when my radius is 24. It's still changing at a constant rate, but your radius is different. Put that in there, you get 3, 4, 5, 6, interesting number, inches cubed per minute. Okay. Let the actual variable tell you what your units are. Volume, that would be a cubic, time, okay, RT. Okay, so thank you, and we are done with our examples.